Okay, so I am practicing to introduce Courtney. This is my practice introduction for the practice talk before the defense so that I don't blow it when the defense arises. So it is my pleasure today to introduce Courtney Schreiner, who's going to be telling us about super cool work she's been doing on transmissible vaccines. Before heading off to one of three possible greener pastures, which is going to comprise spring break, which PhD program to go to. So in all seriousness, I think working with Courtney has been nothing but fun. I think that's actually true. It's been purely fun almost all the time, no pain. So yeah, okay, go. I've really warmed up the audience for you now.
All right, thank you, Scott. Always good to break the ice by laughing at you. Sorry, gotta share my. All right, so today I'm going to be talking about optimizing the delivery of self-disseminating vaccines in fluctuating wildlife populations. So,
maybe just minimize the audience.
Oh, I was like, goodness, a question already. Wow.
I just want to see the slide. Thank you.
Okay.
Now
So,
you've thrown everything off.
I'm like, no. Okay. As we all are now abundantly clear, abundantly aware, emerging infectious diseases are a huge threat to the human population. It's estimated that roughly 60% of human diseases have animal origins. And some examples of diseases other than COVID to care about are rabies, which causes 59,000 deaths per year. Lassa fever causes on average 30,000 deaths per year. And then the Ebola outbreak in 2014 to 2016 killed 11,000 individuals. However, one way to combat this problem of pathogens spilling over into the human population is through wildlife vaccination. So by vaccinating the wildlife, we can then in turn reduce the prevalence of pathogens within the host populations and reduce the prevalence of reduce the risk of pathogens spilling over into the human population. Traditionally, wildlife vaccination is done by either trapping and vaccinating animals or distributing a large amount of vaccine-laced baits. This has proven to be successful in rabies and within raccoon and fox populations, and we've nearly eliminated rabies in North America within these populations. However, rabies still persists in other areas of the world, and our current vaccination strategies don't appear to be enough to completely eradicate wildlife pathogens. Part of this is just the fact that wildlife are extremely difficult to reach to be able to vaccinate. Bats are really difficult to trap and catch. The other difficulty that goes into vaccinated wildlife is most wildlife have some level of seasonality due to seasonal reproduction that creates these large fluctuations in population size year to year. And previous research has found that this can drastically influence the your effectiveness of your vaccination campaign. And so an example of populations that we could be thinking about would be rodent populations that experience large booms and busts in population size. And depending on when we start distributing vaccine, we can end up with differing levels of pathogen reduction. So that is with just standard conventional vaccines like vaccine-laced baits. But recent technology has given opportunity to use self-disseminating vaccines that might be more effective at vaccinating wildlife populations. And so self-disseminating vaccines allow for additional individuals to be vaccinated indirectly. So even though you may vaccinate one individual, you may get additional vaccines for free, so to speak. This also reduces the level of vaccination coverage needed. And there are two main types of self-disseminating vaccines that I'm going to be talking about today, and that is transmissible vaccines and transferable vaccines. So transmissible vaccines behave similar to how a pathogen does and can spread to multiple individuals. So imagine I have some vaccine-laced bait, I randomly distribute into my population, little mouse comes by and munches on this bait and ingests the vaccine, gains immunity, but also becomes infectious with the vaccine. So then when it hangs out with its other mice friends, it then spreads the vaccine to those individuals. And this can create, this has the potential to create self-sustaining chains of transmission for the vaccine. In contrast, transferable vaccines cannot create those self-sustaining chains of transmission. So a transferable vaccine relies on the grooming behaviors of animals. So in this situation, imagine we have a vaccine-laced gel that we paint on the back of an animal, and then through other individuals in the population grooming each other, they end up ingesting that vaccine and becoming vaccinated. But that is the extent to which the spread of the vaccine is. So additional vaccinated individuals can only come from the originally vaccinated individual. So with these self-disseminating vaccines as being potential ways to combat infectious diseases in wildlife, we don't exactly know how these will behave within seasonally fluctuating wildlife populations. So we want to know, does seasonality influence the outcome of vaccination campaigns within self-disseminating vaccines? Does timing matter if we have these vaccines that are capable of transmitting to further individuals? And if so, then under what conditions is timing most important? And for what animals does timing matter for self-disseminating vaccines? Varying animals have different degrees of seasonality, so we can imagine that for some animals, timing might be more important, or either their lifespan could influence that as well. So to answer this, we need to first be able to model vaccination. So the direct vaccination in this is modeled as a step function where vaccination occurs every year at day T sub v and lasts for some length of the vaccination campaign, V sub L. And the overall rate of vaccination is determined by the number of vaccines we have divided by the length of the vaccination campaign. And so if we're within this range of the time of vaccination and the length of vaccination campaign, that's going to be our rate of vaccination. But if we're out of that, then the vaccination rate will just be 0. To get a good visual of this, so on the horizontal axis, we have the time, the day of the year, of which we might implement our vaccine. And then on the vertical axis, we have the rate of vaccination corresponding to that time. So as I mentioned, we want to know when is the optimal time to vaccinate. And additionally, we also want to know, how should I distribute my vaccines? So is it better if I distribute them all at once or over a long period of time? And that's what you can see on the right figure. And this is also assuming that we're distributing the same number of vaccines in each of these scenarios. Additionally, we need to be able to incorporate the host demography or that seasonal reproduction. And we do this by using a periodic Gaussian function, which is derived from Alison Peel and others. And this describes the rate of births within the population. And this gives us a lot of flexibility to parameterize and look into different host wildlife with differing seasonal reproduction. And so S here controls the level of seasonality, or how synchronized are the births. Are they all occurring at once, or are they spread out through a larger range of time? And then we can also control the peak of the birth pulse if we want to. So if we want it to be later in the year, we can do that through T sub P. And then this function has a period of 1 year. So this birth function will repeat every year, or every 365 days. And then K is a scaling factor that we can use to control for the average population size. So again, just to illustrate what this function looks like. So again, that degree of seasonality, or just how synchronized those births are going to be, is represented on the left panel. And higher values of S correspond to higher seasonality, versus lower values of S would be less seasonally forced populations. And then again, on the right, we can move this birth pulse to be at any point in the year. So now with the vaccination function and with the birth function, we can begin to put this together into an overall model. So what I used here is a susceptible, infected, recovered framework, or an SIR framework. And I developed two models, one for the transmissible vaccine and one for the transferable vaccine, since these behave differently. And so first we'll start with the transmissible vaccine model. So we have four classes, and these are our susceptible individuals, our pathogen infected individuals, or our vaccinated individuals. And these individuals are immune to the pathogen. Or we can have recovered individuals, which are immune due to recovering from the pathogen or from the vaccine. And so what I mean by recovering from the vaccine is the fact that vaccinated individuals don't maintain their ability to spread vaccine for indefinitely. And so they lose that ability, and that is essentially them recovering, and they just maintain their immunity by moving into the R class. So to start, for the actual equations, we again see our birth function, B of T, all individuals are born into the susceptible class. And then for the transmission of the pathogen, beta P of susceptible individuals coming in contact with pathogen infected individuals move into the pathogen infected class. Additionally, you can be infected by the vaccine at a transmission rate beta V of susceptible individuals coming in contact with vaccinated individuals. Now for direct vaccination, so this vaccination rate determined by that vaccination function, but here we multiply by 1/n to account for the fact that any individual could be consuming baits, and this will deplete the actual number of baits in the population. And we only want to track the proportion of susceptible individuals. So that is why that is there. And then we can, or individuals can recover from either the pathogen or the vaccine, as previously mentioned, and this is represented by gamma, either gamma P for the pathogen or gamma V for the vaccine. The other way that you can be lost, or the ways that you can be lost from the system, is either through natural mortality, determined by D. We assume this to be constant, or through the virulence of the pathogen. All right, on to the transferable vaccine model. So this is relatively similar to the first model, but we have two additional classes. So we still have the standard susceptible, pathogen infected, and recovered. But now we also have the P sub G and R sub G class, which represent individuals that are pathogen infected and have gel on them, and recovered individuals that have immunity and have gel on them. So again, the same start, birth function and the pathogen dynamics. However, now we have the additional P sub G, and this is because if you come in contact with a P sub G individual, you can either get the pathogen or you can receive the gel instead. And so P sub G shows up in the both of these mass action terms. The underline in red being the pathogen dynamics, and in blue we have the transfer of gel, and that can occur from either gelled and pathogen infected individuals or recovered and gelled individuals. Now, with the vaccine, so one of the main things to note here is we do not care what class individuals are in for them to be gelled. If you're an individual in the population, I can paint gel on you and you can effectively spread my vaccine for me. And so because of this, that's why we have the P sub G and the R sub G. But the susceptible class does not have a gelled class, because we assume that if you're going to take the time to pick up an animal and it happens to be a susceptible individual, you're going to also manually vaccinate that individual. And so the susceptible gelled individuals go directly into the R sub G class, in addition to recovered individuals that become gelled. And so the other assumption here with vaccination is we are not multiplying by 1 over n, we're multiplying by 1 over s plus p plus r. And this is because we assume that we can recognize gelled individuals. So if I pick up an animal and it has gel on it, I'm not going to put more gel on it. And so we don't need to take into account that depleting the vaccines. A new term for this model compared to the last model is that because individuals are grooming each other, they are also effectively taking gel off of individuals by grooming each other. And so there is a limited amount of gel on an animal, and we need to incorporate the fact that by other individuals in the population licking a gelled individual, this will remove gel and they move back to their respective class. And then again with recovery, so the alpha in times PG or RG takes into account the licking, but for like licking gel off. But here recovery for the gelled individuals represents the gel is no longer effective. So the gel doesn't remain effective on the back of an animal for a long period of time. And so that is why we have the gamma G recovery of gelled individuals back into their respective classes. And then we can also have recovery gamma P from the pathogen infected class moving into the R class. And then lastly, individuals can leave the system due to natural mortality or virulence, as they did in the transmissible vaccine model. So those are the models. And so with those systems of ODEs, we can then numerically solve those. I numerically solved them in R. And now we want to evaluate the effectiveness of a vaccination strategy for a given time of vaccination and a given length of the vaccination campaign. And to do this, we calculated the average level of pathogen reduction as the average number of pathogen infected individuals without vaccination, X sub naught, and minus the average number of pathogen infected individuals with vaccination over the average number without vaccination. And these averages were calculated over a 10-year period. So what is the average level of pathogen reduction if I vaccinate every year for 10 years? So now into the results. So in most of these figures, pretty much all of them, it will be time of vaccination on the x-axis or horizontal axis, and then the pathogen reduction on the y-axis. And so a point on this plot or on these lines represents the level of pathogen reduction achieved for those times of vaccination. And for this, I'm just assuming for this one, we're also considering different lengths of the vaccination campaign of what we think are actually feasible of 1 day, 1 week, or 2 weeks. And so the first thing to notice here is timing indeed matters. Before I get into that, the birthing season is represented by the Gaussian-looking gray curve. So timing, we can see that timing matters by the fact that there are times in the year of which the level of pathogen reduction is either 100%, so we pretty much have eradication, or times of year when the level of pathogen reduction is only 25%. Same with the transferable vaccine, a difference of either a level of 75% pathogen reduction, which is still huge, compared to a 25% level of pathogen reduction. And so we can conclude timing matters. In addition to that, we can see that timing matters more for the transferable vaccine than the transmissible vaccine by the fact that if you're vaccinating with a transmissible vaccine at some point in the birthing season, you can achieve a super high level of pathogen reduction. Whereas with the transferable vaccine, there's a very distinct maximum to achieve your highest level of pathogen reduction. Interesting enough, the transferable vaccine, this is delayed to slightly after the birth pulse. And a lot of the difference for this can be attributed to the fact that transmissible vaccines can spread to, can create those self-sustaining chains of transmission. So if you're distributing a transmissible vaccine when this birth pulse is just starting to pick up, you're having a large influx of new susceptible individuals, and the transmissible vaccine can keep up with that birth pulse and effectively spread your vaccine through the entire birth pulse. Whereas the transferable vaccine cannot. So in order to vaccinate the highest number of individuals, you want to wait until there's the most susceptible individuals in the population to maximize the number of individuals you'll be able to vaccinate. So then now we'll talk about the effects of R0. I think most people in this room understand R0, but here we're thinking of a completely naive population with a single infected individual, and on average, how many additional infections result from that singly infected individual. And we can talk about R0 in both respect to the vaccine and the pathogen. And so now in these figures, we have plotted the transmissible vaccine in black, and then the transferable vaccine in red, and still the birth function and the same setup of the axes. But instead, we have the situation where the R0 of the vaccine is either greater than the R0 of the pathogen, or the R0 of the vaccine on the right, the R0 of the vaccine is less than the R0 of the pathogen. Here, for these simulations, the R0 of the pathogen is 2 in both of these figures. And so this kind of gets out of like when timing matters versus when it doesn't, and for what types of self-disseminating vaccines doesn't matter. And as we can see, first off, the transferable vaccine in both of these scenarios, the timing still matters, and is still slightly after the birth pulse. But the transmissible vaccine, timing doesn't make a difference when the R0 of the vaccine is greater than the R0 of the pathogen. However, when that's not the case, when we have the opposite, then we want to time our vaccine appropriately in order to achieve the highest level of pathogen reduction. The way I kind of think about this is the vaccine and the pathogen are kind of competing for susceptible individuals. And when the R0 of the vaccine is greater than the pathogen, it can perform better than the pathogen. And so no matter when you implement it, it will spread to more individuals than what the pathogen can. Whereas when the R0 of the vaccine is less than the R0 of the pathogen, then when we're looking at the level of, or like the pathogen prevalence before we start vaccinating, then the pathogen is really low and we're going to drop a lot of our vaccines all at once. And so this gives opportunity for the vaccine to spread to the incoming susceptible individuals before the pathogen can. And that's when we get these high levels of pathogen reduction. Whereas if we wait until late in the year, the pathogen has essentially infected most of the new susceptible individuals. The last thing I'll talk about is lifespan. So as I mentioned, we could be talking about a lot of different wildlife for these self-disseminating vaccines. And one thing to consider is whether we are talking about wildlife with very short lifespans or low population turnover versus animals with longer lifespans. And so what we can see here is that the lifespan, that timing matters for short-lived organisms. So this is the black line of lifespan of 1 year. And this is due to the fact that these animals have a lot of population turnover. So when you vaccinate in 1 year, all those individuals you vaccinated are likely to be gone by the time you vaccinate the next year, and then you have another large influx of susceptible individuals. Instead of, if you have a lifespan of 5 years, then most of those individuals that you vaccinated in the years prior will still be around, and you can gradually increase the level of vaccination coverage. And yeah, I think it's interesting to see that even the transmissible or the transferable vaccine, you still get that timing doesn't matter with a lifespan of 5 years or more, you'll get the same result. So from all of this, we can conclude that seasonality or the seasonal reproduction strongly influences the outcome of wildlife vaccination. And timing is important for weekly transmissible vaccines. That is when the R0 of the vaccine is less than the R0 of the pathogen, but is always important for transferable vaccines. Additionally, timing is most important for animals with short lifespans or a lot of population turnover. And my acknowledgements, I'd like to thank all the individuals in the Nuismer lab, although some of them aren't in the Nuismer lab, but they were here when I did the bulk of this. Especially my advisor, Scott Nuismer, and Christopher Mean, Andrew Basinski, and individuals in BCB and other friends and family. So thank you. I'll take questions now. Barry? Yes.
Okay, so could you convert your findings to some kind of common biological, like use case examples of animals and spillover diseases? Like, so what animals and spillover diseases would have, say, a short lifespan and seasonal reproduction where it would change how you were employed?
Yeah, so the first thing that comes to mind would be Mastomys natalensis and loss of fever. They have strong fluctuations in population size, and loss of fever frequently spills over into the human population through these rodents. So that would be one potential application.
Are there others that we would be worried about in North America?
None that come immediately to mind, unless Scott has ideas.
No.
Four corners, perhaps.
What are you thinking?
Hantavirus. I was going to say,
Oh, yeah.
Hantavirus.
Yes. Sorry, I was,
We
yeah.
have that here, don't we? Or do we worry about that?
Good word.
Okay.
Last one.
Yeah.
So that was fun, first of all. So the seasonality that you have in the model is driven by fluctuations in birth rate.
Yes.
And I agree that's probably really important for a lot of animals. But another way animal population sizes might fluctuate is by major fluctuations in death rate.
Yes.
Instead of birth rate. Do you think you'd get the same result where you want to vaccinate when the population size is the largest, or do you think it would be totally different? Or
I think it would still be the same. I think, like, in general, my takeaway from all of it is you want to drop your vaccine when you have the most susceptible individuals in your population to maximize the number that you can vaccinate. Additionally, if you vaccinate when your population size is low, you end up just wasting a lot of your vaccines. Paul?
The basic model is basically assuming sort of well-mixed
Yeah.
populations, randomized population structure. Transmissible vaccines and then transferable vaccines are really affected by technique. If the species, if they only grew their those family members or something, so super
Yeah, totally.
population structure.
Yeah.
Like for the Lassa fever, it was able to keep going.
About their what?
Grooming behavior, like
Grooming?
whether transferable vaccines would be feasible.
I assume so. I'm not that familiar, I guess, with their actual behavior amongst the animals. But to my current understanding, they generally mingle somewhat, so I think it would still be effective.
What somewhat?
Mingle.
The word she used was mingle.
But like that would be a problem with bats. Bats tend to have like a hierarchy of like where they hang out within the roosts, and they tend to only like hang out with individuals next to them, and that would be yeah. So, and for some reason, I started getting really interested in bats, so I know a lot about them. More than the rodents.
I have another question. In terms of, you got a couple of graphs of kind of scenarios. One where your vaccine was more transmissible than your disease, and the opposite. But I mean, again, I'm getting down to example cases of this. Like, is that controllable? When you try to engineer a transmissible vaccine, is this a thing where they try to engineer it so that it's as infectious as possible, or do they just get what they get?
I think right now the current goal with the development with those is just to get them to actually work, not necessarily critique them to be a certain way. But this at least allows us to know, like, okay, if we have this type of self-disseminating vaccine, this is how we expect it to play out.
I mean, do they have any?
So transferable vaccines, there's been one study by someone you all interviewed, Daniel Baker. No, wait, what's his name? I'm confusing Kevin Baker and Daniel Stryker. Confused the two. But they did a model of transferable vaccines and actually went out and captured bats. And what they ended up using was just a fluorescent biomarker. They didn't actually develop a vaccine, but just said, like, okay, if we have this population, say we had a transferable vaccine, how well would it do? And it did pretty good. And like they effectively, I think they averaged, like it spread to like an additional 2 individuals for every one they put the fluorescent biomarker on. So that's one case of the transferable vaccine.
But that's not the same as an R0 because it stops, right? Like, put the gel on one.
Yeah.
It's transferred to 2 others, but then those others don't keep it going.
Yeah, they do. Yes.
I'll ask another related. So for the transmissible vaccines, what duration of infection were you assuming for
the transmissible vaccines?
Yeah.
So for these, I made the transmissible and the transferable vaccines equal in the sense of they were both 21 days.
So fairly fast. I'm just thinking of,
That's funny because if you like, sorry.
I mean, it's slower than like maybe a respiratory virus, but it's faster than, I was thinking of CMV, right? Where
Okay, yeah.
it might, like, it's weird because it might go late, but did you play around with duration of infection?
I have, yes. I haven't gotten to play around with it since we updated the transferable model. But typically, your vaccine does better if the duration is shorter, because we're holding R0 constant. So if you make gamma larger, then you're also making beta, and I get confused, but
You're focusing on the additional.
yeah. So then essentially it moves through the population faster.
Yeah.
Essentially.
I'm just wondering if we're screwing up with CNP-based vector vaccines if they're really slow, right?
Yeah. So that's in the current paper. It's figure 4.
Figure 4, Chris.
I just haven't gotten to redo it with the new equations for the transferable vaccine, which things didn't really change with the additions that we made, except what's more so the bigger thing of the change in my results is previously we're using far too many vaccines for the population size we had. And so now kind of the results are dwindled a little bit, but that's just because I'm using a more realistic level of vaccines. So yeah. But yes, if you're infected with it longer, it doesn't do as well as if you're infected with it shorter.
I guess I have one more kind of question. It's along the same lines, converting your mathematical results to sort of more plain language, kind of accessible terms. Because you frame things in terms of the percentage reduction. And I'm just wondering, like, does that translate in some intuitive way to spillover risk or the health of the wildlife population or something that's a little bit more accessible to dumb people like myself? You know what I mean?
You're
Or
not
is it
dumb.
just so complicated that
I mean, you can think of it as like like it's adjacent to the pathogen prevalence. So if we have a high level of pathogen reduction, the overall like amount of pathogen in the population is less. That helps.
No, I get that it would be related to that, but it sounds like it's not easy to translate. You have to get in much more case specific. So that means in this case, the risk of a spillover is lower. But you can't make those claims without.
Yeah. I'm not sure how we could make those claims.
All of my questions sort of stem from the fact that I think this is like super cool, and I think that you really did a really good job. But I would advise you, if you're going to do this presentation again to a more like people that where there is a more general audience, that maybe you should bring back like in the front who had loss of fever and rabies and some other third thing I can't remember.
It was Ebola.
You're right. If you bring those back as like examples of application of what we've just learned, for example, in loss of fever, these organisms have this lifespan and they are seasonal breeders, and it means that these kind of findings matter. Whereas for one of your other examples, the organisms live so long that the time is less relevant.
Yeah.
For a person like me, that anchor point would matter a lot in terms of remembering stuff.
Yeah. Okay. That's definitely in the plan of things to do.
Because that's what I wanted to know. This is a good thing. Right? I was like,
Yeah.
well, what's this mean?
Yeah. Yeah. Great.
Well, I think we can head up the hill. Thank you very much.
Yeah. Thank you.